Hello everyone, welcome and thank you for joining this QTNano Talks. So today we have the pleasure to have here Professor Michael Piai Lourenço from Federal University of Espírito Santo. He's going to talk about AI in material science and chemistry. So thank you, Professor, for accepting this invitation and giving this talk for us. Just a reminder before we start that you can leave your questions or comments in the chat or wait to the end of the talk, so to raise your hand and ask with your voice or question. So again, thank you, Professor, and now the stage is yours.
Okay. So thank you for the invitation from Professor Juarez. Thank you, Rafael. And so we are going to talk about the quest for automation for structural elucidation of materials in the molecular clusters. So let's go. Okay. So when we think about artificial intelligence, first we have to think about the chemical space. So the chemical space is everything that we try to do around the world as chemists and as scientists in this field of material science, for instance, or molecular physics. I mean, we wish to get new materials, we wish to understand mechanisms, we wish to design new catalysts, whether in homogeneous or heterogeneous catalysis. And so we play with the periodic table for new compounds, organics, in organic chemistry. And we manage the variables to get new experiments. And we also wish to do structural elucidation. So everything of this is the chemical space, which is huge, around 10 to 100. And it's huger even than the number of atoms in the universe. So here we are going to show by bringing two problems we are going to show from these two problems how AI can help us to provide automatic structural elucidation of vacancies, problem 1, and the problem 2, automatic structural elucidation of molecular cluster by using genetic algorithm. So we have here the problem 1A, which we are going to discuss artificial intelligence to structural elucidation of vacancies in carbon allotropes and perovskite oxygen vacancies as well. So problem 2, we are going to show you some results by using the DFTB in the genetic algorithm for the water 20 molecular cluster, water 10, water 20, and the sodium with water 20. So that is our problem that we are going to tackle and show you the methodology involving artificial intelligence here. So about the water, it's quite interesting. I'm reading this Alan Turing biography, and at some moment of the book, it's mentioned that Turing tried to do research in water from the specialist at that time, in the last century, Fowler, and Alan made no progress by working with water. Water is very challenging, we know. And so Alan gave up of water, but he gave us the machines to model water. It's quite interesting. So, but what do we want with artificial intelligence? So I like this analogy that I'm going to bring to you. There is an account of Jorge Luis Borges from Argentina, writer. And there is the account, which is the name of the book also, which is the Aleph. And the Aleph is defined in this count, which is beautiful count, is one of the points in space that contains all other points. And I believe that it is what we try to do with science or math modeling, and even, of course, statistics and artificial intelligence. We wish to find some models that we can tackle and follow all of these points in space. So, and one nice moment of this country is when he saw the character saw the Aleph. I saw the Aleph, that secret and the conjectured object whose name is common to all men, but which no man has looked upon, the unimaginable universe. So maybe that is what we wish with AI. So I try to actually follow my career thinking about this question that I made to myself. How to deal with the infinity by knowing so little about the finite? May we get inspired by ancient Greek literature and invoke the god of automaton or automation? Yes, we wish so. So Hephaestus, it's nice because Hephaestus was a Greek god, and it was one of the first times that the automata or automation word appeared in the history of humankind before Christ. And Hephaestus was a god of the work, and he worked in a forge, and he built robots to called automatons to help him to do his swords and the shields for the gods. And it's quite interesting. So we wish to invoke this god of automaton to help us to tackle this infinity. So I'm going now to talk about artificial intelligence by using the active learning method. How I see artificial intelligence by thinking in a chemical problem. And this sum up here will show us during this talk, as we will see, what I wish to solve. So here we have this alloy, which is doping silicon by aluminum. And we have 330 possibilities. And we have here all the possible computations and the total energies from DFTB calculations in this case. DFTB calculation, actually it's a DFT based on tight binding. It's approximated method that I have worked since my PhD studies. So here we have the black distribution with all possible structures. But of course, we don't always have resources to do all possible combinations of isotopes of this alloy. So what we wish to do with AI is to get a small sample, which is this blue one here, from random, and try to get the smaller energy here. So we wish to go from here and find some way in order to go to the left here with fewer computation as possible. We are not interested in describing this distribution correctly. We just wish to get this data and come from here to there. That is our goal. And we are going to show how we can use methods to do this jump. So what is supervised machine learning and active learning? I'm going to discuss both methods here. So let's think that we have some measurements in the laboratory where we have the P, the pressure of CO2 gas, and we are going to perform measurements of the pressure and the volume, and we have as response the temperature. So in this case, we have 5 measurements and of course 5 responses. So in machine learning, we call this variable the descriptor or the features. And the T in our case here, as I define my problem, is our target or objective function. So we have this surface. Of course, it's a simple problem, but it's a gigantic one. So my goal is to get from these 5 data here and maximize my temperature with few experiments as possible to come from here to there. So how can we do that? That is machine learning. So we have now from this data, of course, it's not machine learning yet. We just have the data. And here I set up my problem. But so with machine learning, now it's machine learning, I get these 5 data here and we create a regression model. In this case, actually it's actual results. I made this from another software that I have, which is called Machine Learning for Chemistry. In the end, I can mention briefly about that. And here we have the neural network with bootstrapping for uncertainty quantifications. So we started with just these 5 data here. The blue one are the training data, and the red one is the testing data from neural network. And from the bootstrapping, I just resample this 100 times, and I have 100 neural network regression. From that, I get the mean and the average. And this average, as we can see here, is the uncertainty. And the green circle here is the mean from the prediction. And here the standard deviation, which is the uncertainty. So now we have the machine learning model, where here in the x-axis, we have the observed data, and here the predicted data, the y-axis. So that's the step 0. Now, I can get some points in the virtual or unexplored space. And these points here from P and the V are not observed yet or computed yet. And now we have these 3 points. So we have here, this one here for pressure 6 in the volume 30 here. And then we have for 9 and the 10. Here is the pressure 9, and here is the pressure 10. The volume is the same. So if I get this data here, of course, when I wish to maximize, I wish to go to the blue star. So if I just think in prediction, which is this mean from the 100 model, I would get this one with higher temperature to try to do the next experiment. Here in the 10, the prediction gives me a mean, or the prediction is smaller with smaller temperature than this one. So I would pick this if I just consider the prediction, the pure prediction, which we call exploitation. But if I consider the uncertainty, which is the exploration to go farther to the potential energy surface where we wish to go, or the search space, in this case, I consider also the uncertainty. So the uncertainty plus the prediction would be the better point that I would tackle, would get to do the next experiment. And I do so, I can compute this point here, and in just one step, I can get the global maximum here within my defined search space. So that is active learning. When we use regression to get the prediction, which is the exploitation, plus its uncertainty, which is the exploration. And we are going to show from acquisition functions or decision making, how we can use exploitation and exploration to do this search on the unexplored space. So if you continue, we are going to do these steps, even by finding the global maximum that I was interested in, the maximum temperature, I can have better models, the training and the test set. And the question is, what did the machine learn with this data? The van der Waals equation for a real CO2 gas. So now we have a picture of what is machine learning and what is active learning. Active learning uses machine learning with uncertainty and the prediction to make inference for new discoveries, experiments. So now that we have this abstract or of resume of this method, let's apply that for vacancies. So we have a software which is called QMLMaterial, a quantum machine learning software for material design and the discovery. And we have the implementation in this method, a lot of possibilities of automatic structural elucidation by using active learning. And here I'm going to present to you the recent results of this method applied for vacancies. So The QMLMaterial actually can be thought by this scheme. So let's say that we have a atomic cluster which is sodium 20, just an example. And I have this sodium 20 cluster. We randomly get 20 initial structure, which is my initial population or initial database. So here I have this 20 and I perform DFT or DFTB calculations from these 20 random isomers. And after that, we get from this 20, the machine learning regression. From this regression, I have a machine learning model. And then now here I use from this step to this step here I have the part of the decision making in the step C. So step A is the sampling, B is the calculation, and C, we have the decision making, where we use machine learning and by the exploitation and the exploration by using the expected improvement. So I got these 20 initial random structures, and I do some mutation or crossover from genetic algorithm operators, and I create an unexplored space. So let's say that our unexplored space has 500 structures, not computed, just structures from plain cut splice or GA operators or mutation. Now I apply the machine learning regression from this 20 and I try to predict these 500 structures and the compute the uncertainty. So from that, I compute for these 500 structures, the expected improvement. And I select the structures in this 500 space with the 20 highest expected improvement to do the next calculations. So I create the structures from this new 20. This is new. Let's put that this is star. Now from the expected improvement, I compute that, and now I have 20 plus 20 star. And now I have more data. My machine learning regression will improve. And I generate again more structures in the unexplored space, apply the expected improvement, which brings exploitation and exploration. And the cycle, and I compute another 20, and the cycles goes on until we find the global minima structure. So that is the active learning. And we can apply that for molecular clusters. Sorry, atomic cluster. This case here is atomic cluster, sorry. And we can apply that for doping and the vacancies. So that is, but one important thing by AI is actually the environment plus the agent. So what is the agent? The agent is this decision making here, where we use data to make decision in the unexplored or virtual space, just 500, for instance. And then the environment is everything. Is the part of the DFT or DFTB calculation, is the part where the structures are generated. I mean, the inputs of the program are generated here in this step A. So everything is the environment, and the part where we have the machine learning and the acquisition function for decision making here, this is the agent. So we define the AI based on active learning. So here I'm going to discuss more about the expected improvement. So here we have the exploitation. Exploitation performs global search, local search in regions that the potential energy surface is known. And from the uncertainty, we have the exploration. That can give us ways to go further to the potential energy surface in explored space. And here we have the cumulative density function and the probability density function, which are statistical functions, and it will balance the amount of exploitation and the exploration based on this wave here. So here we have that a surface plot, a limit surface, where we have here the exploitation and the exploration and the values of the expected improvement in this range here. So what does that mean? It means that we are going to get those structures in the unexplored space. And those structures, of course, they are described by descriptors, which are these axes here. Okay. J means that we are in the unexplored space. And here we are going to always try to get those descriptors or structures where we have the higher exploitation and the higher uncertainty, which will give us the higher value of the expected improvement. So for example, here we have the blue training data, red testing data, and the green, the virtual space, the points that were not observed yet. And here we have the global minima. So in this case, we are going to get the green point where we have the higher uncertainty and the prediction closer to the global minima, or I mean the maximum value. Of course, we don't know the global minima, but always the value which is higher. So we pick this point and the compute, we can get closer to the global minima here. So that's the idea of the expected improvement. It is an acquisition function. It comes from the decision making in artificial intelligence, and it also is used in reinforcement learning, which is well used, and it got more famous after the Go game from the DeepMind, solved by reinforcement learning. Active learning, I see that it's quite similar to reinforcement learning. Of course, there are some differences, which is not our proposal here to bring, but it's quite similar. So applications. So we have here this problem. Free carbon vacancies in a unit cell of graphite with 36 carbon atoms. The chemical space, of course, it's a discrete search. We have around 7,000 possibility. For C60 in the 4 vacancy, we have around 500,000 possibilities in a discrete search without considering symmetries, of course. And here we have the results from applying the QMLMaterial, where we have implemented the active learning. So for graphite with 3 vacancies, we started with just 500 structures, and we have 20 independent ones. It's interesting because these 5, for which one of these independent ones, as the method is stochastic, the active learning, from these 20 independent ones, every time I just, with the same input, I run the active learning, a new sampling from random sampling with different random structures are generated. I mean, these 20 independent ones were done in a way that the initial population is random and different from each independent one. So in this case, we can contemplate the powerful of the method in dealing with different initial distribution of the random structures from these vacancies. So we have here, for example, we used the expected improvement. We used another acquisition function, which is called the lower confidence bound, by changing the degree of the uncertainty with 1 to 5, random search. And here we also used different descriptor. The descriptor here is the L-out-Sum matrix and the sign matrix here, L-out-Sum matrix and the sign matrix for periodic systems. And we even compared it with GA. So what is this cumulative success? So we know the global minimum in this case. And this cumulative success is the number of times in the 20 independent ones, the global minimum was found as a function of the new local optimizations. So we can see here that with the the lower confidence bound and the expected improvement, they bring similar results. And with just 100 local optimizations, we can find the global minimum in just 20 independent runs. So we can compare with the random the GA, which is this green one. We have a GAMaterial, which brings GA for vacancies and the doping, and we use the code. And here we have the GA. So the better performance is from the expected improvement. So here we have other comparisons. So for the C60 with 4 vacancies, we use the MBTR descriptor. Here now we have a molecular system. I mean, here it's a solid. I use a descriptor for solid. And here we use the MBTR for molecules. But of course, we can use for solids as well, MBTR. So here we have different kernels of the Gaussian process. The regression that I used was Gaussian process, machine learning regression. And I compared with random search and the GA, and the active learning performed better. With just few local optimizations, we could find in 20 independent runs the global minima. It's interesting because I believe the machine learning with the descriptor, somehow even the full chemical space being huge, I guess that somehow the machine learning and the active learning method iteratively, they are somehow, I believe, contemplating the symmetry without considering explicit symmetry in the problem to reduce the search space. This is just a thought. I did not prove that, but I have this impression. So the last application for vacancy is oxygen vacancy perovskite by using the QuantEspresso DFT. Here I use the DFTB method, which is cheaper than DFT, and we can tackle huge systems. And here I have the problem of oxygen vacancies in perovskites. So my search space is 2000, around 2000. And we fewer calculations to find the global minimum structure. So we performed the 3 independent runs by starting with 90 random vacancies of oxygen. And from that, we created the machine learning regression and performed the active learning. And we could find in all 3 independent runs the global minima. The descriptor here is it's putative. We don't know if it's actually the global minima, but it's the putative global minima. Here we use the Elwood sum matrix. That is the structure with the vacancies here. That is the global minima. So here we have the regression to show to you here. When we have 200 structures, and when we found the global minima by the active learning in set independent run. So the training in the test, we can see that the regression model is quite good. So here are the indexes of the vacancies of oxygen, that is our putative global minima. So here there is this interpretation of the structure. We could see that by removing oxygen, we saw a reduction of the titanium sites, and the coordination number also reduced from 6 to 5. We could see 3 chemical environments, titanium 4, 3, and the 2, due to the oxygen vacancy. And when we plot the partial density of states, we could see these states here that are from these different environments of titanium. But one interesting news from this result is that here we have the putative GM, global minima. And here we have some random structure that I just got by hand when starting to do this work. So I've got some structure from this perovskite and I removed it randomly by hand, 3 oxygens in my unit cell. And I performed the DFT from QuantEspresso calculations. And I performed the PDOS. It is metallic. When I do the search by using active learning or AI, we have another structure which is our putative, and here we have the behavior as P semiconductor. What does that mean? It means that if we wish to work with non-stoichiometry and even create databases like the material science or material gen, we need actually for non-stoichiometry, we need actually to have structures at least closer to the putative global minima to have correct electronic properties. Otherwise, if you just get vacancies or defects, even doping, by chance, we would go in the wrong property. We would have the wrong property because we are farther to the global minimum. So, I mean, it's necessary for non-stoichiometry and defects modeling to use active learning or the QMLMaterial. Okay, now we have the problem 2, which is the GAMaterial for genetic algorithm, in particular for this presentation, molecular clusters. So this GAMaterial is a genetic algorithm software for material design and discovery. It's like a broader of the QMLMaterial. We get inspirations from active learning and the GA active learning to try to do this kind of work. It's nice. So this work is in the final edition now to be published. We have the DOI already. And here we have the workflow. And this publication was just for molecular clusters and the vacancies, and the doping. We have a lot of features. And I will show to you later the capabilities of the GAMaterial. So it was, it's going to be published soon. And but we published it just for molecular clusters, atomic clusters and the defects in the interfaces. For molecular clusters, it is in progress for another work. So what is the GA? In this case, we get some random structures. It can be defects like doping vacancy or atomic clusters, or even interfaces, clusters on surfaces, for example, or surface reconstruction. We get that randomly, perform some DFT calculation or DFTB, get the population, perform selection for crossover in the mutation. Here's the selection. After the selection, we perform the GA operators, and then we have a new selection from the pool of structures in the unexplored space from the crossover or mutation. Here we can get the structures randomly or even use machine learning. Machine learning is inside the GAMaterial. So the cycles goes on. So again, this workflow is the general workflow for genetic algorithm, as in this particular case implemented in the GAMaterial. But we wish to go further to problems involving vacancies or doping and atomic clusters and its interfaces. We wish to go to molecular clusters. So we have a newer version of the GAMaterial where we implemented the global search for molecular clusters, important for microsolvations and adsorption on surfaces and things like that, as I will show you. So what is the operators? How are the operators behind the GAMaterial for molecular cluster now? Like water 6, water 20, whatever. So here we have the molecule A, B, and the C. So very diverse the structures. Here we have the father, and on the right we have the mother. And what we do here, we just get some binary list with 1 and a 0. So when it is 1, it means that we are going to exchange for example, here 1 is in the A molecule. So we exchange the A from the father to the A prime of the mother. So B, no change will happen. And then the C, we have change because we have the 1. So we exchange the C with the C prime. So we get, in this case, the crossover, and we have the offspring. After doing this, we join the two structures to get the offspring, we get this substituted A, where we substitute A prime to A. So we just perform some rotation and a translation. I mean, we do this mating and perturbate a little bit the molecular cluster. So A prime substitutes this A, B is kept, and the C prime goes to here. And after it goes to here, we perform some perturbation by rotation and the translation. And we have here a random value between 0 and 5 by multiplied by this random rotation and this random translation. So we have the input here, the input in the GAMaterial software. We can say the range of the alpha, beta, and the gamma angles, and also the mean value and the maximum value of the angles that we wish to rotate the molecule, based on the center of the mass of the molecule. And we also have the translation from -3 to 3, like a box. That is the crossover. So we have the mutation, it's important in GA. In this case, we just get one molecular cluster, and we also use the binary list. So, and the ones with 1 will be slightly changed by rotation, its coordinates by rotation in the translations. So A is kept, because it's 0. B changes by this perturbation on the structure, and the C changes as well. So we always get from 30 to 60 of the molecules into the molecular cluster to mutate or to mate, to crossover, like here. So between 30 and 6% of the molecules inside, randomly between 30 and 60, are selected to do this mating or mutation. So now we have some in progress results. So we have, I've worked with the DFTB method, which is a tight binding based on DFT. It's parameterized, it's very hard to parameterize that. And we have some parameters published in 2 years ago, the GCTC for bulk water and some clusters of water as well. And we use these DFTB parameters to do these calculations by using the new implementation of these molecular clusters in the GAMaterial software. So here we have the results for 3 independent runs for water 10. So we can see here that I performed 120,000 local optimizations. And here we can see that we need much higher, we need a greater number of computations compared to atomic clusters, at least by using my DFTB potential. And here we have the final 3 independent runs, and here we have the structure, which is in the smaller structure in the initial database. The population here is 60. So this configuration here is the smallest configuration of the molecular clusters for water in the initial database. So now these 3 structures here, they are here. This is the putative GM. We can see that the energies difference are in the order of milli-electron-volt. It's quite small. So we have here the structures of water 10. We did the same by using machine learning until 5,000 local optimizations. And we did not progress because actually, as we have a lot of local optimizations and the number of structures gets higher, it almost blows the memory of the computer. So I need to fix this problem to continue to see if machine learning can help in accelerating this GA for molecular cluster, but it's implemented. Here we have even nice training in the test set for 6,000 water 10 isomers for using the MBTR descriptor. We can see that the regression is quite good for this free here, which is the just here, the dashed line. So now we have water 20, which requires, of course, much more local optimizations and the GA cycles to get closer energies in independent runs. But here we have some progress. It is in progress again. So that is the configurations in the initial database, the smaller energy. The population here is 60. And here we have the smaller energy found so far, which has this configuration here. So sodium within 20 water molecule. Here we have around 40,000 local optimizations in the GAMaterial. Here we have the smaller energy in the 100 initial population. The initial population was set up randomly. And here we have the putative global minimum found so far. It's interesting because you can see that the water molecule are forming around 2 shells around the sodium ion. And here we can see that we have, so the molecules are above like that, and here they are getting around the sodium. It's quite interesting. I mean, it's like forming a second shell of water solvation. So where are we going? So the QMLMaterial has so far a lot of capabilities, and of course more will come. And we have the global search of atomic clusters. We have results that due to time we could not bring to here, but we have the GAMaterial where we can do the global search of clusters, and we have also the capabilities of doing the global search of the cluster plus the spin multiplicity, the optimum spin multiplicity. I mean, the active learning for molecular cluster, atomic cluster can get you the global minima plus the optimum spin multiplicity. I mean, the search contemplates the electronic part and also the structural part. We have doping in cluster, which also includes the search with the spin for clusters. For solid, we haven't done that yet. We can have doping in clusters in materials. We can have vacancies. We can have doping in the vacancy. It is in progress. So this 1 is already published. 2 is already published. 3 is already published. This is implemented, and we are working with some collaborators from Canada by doing this doping and the vacancy in nickel, in Syria nanoparticle doped with nickel. We have also published here this surface adsorption of particles like C60 on anatase titanium oxide. We have also clusters encapsulated. And we can even do surface reconstruction or even clusters on surfaces. So those are the capabilities of the QMLMaterial. The GAMaterial, we have the capabilities, which is the atomic clusters, doping and the vacancy in materials or nanoparticles. Vacancies, we have encapsulated clusters and the surface reconstruction. All these 1, 2, 3, 4, and the 5 is already contemplated in this publication that is coming soon. And this new one that I present to you will be for another work, I hope. So that's it. I'd like to acknowledge the Universidade Federal do Espírito Santo, the fellowship agency of our state in Espírito Santo, Professor Denis Salahub, where we have developed these softwares, and we have developed the active learning and the AI algorithms for chemistry, and Professor Dennis is the main developer of the demo 2K software, where we use it intensively in our QMLMaterial and the GAMaterial for DFT. We have Professor Patricia Calaminici and Andres Costa, the Alain from NRC of Canada, Elisandra, where she has doing her PhD in active learning by using our softwares, and Irka, which is a postdoc, which also is helping a lot with this development. And I haven't mentioned, but I have also a software which is called MLCam 4D, where I use it for the Van der Waals potential, and this is for experimental design. When we go to the experiment and we have to tackle some variables for synthesis and the prediction of new materials, we can use this software that we are going to work, and we are now working for global optimization by using AI as well. So thank you for your attention. And I end this talk with one of my scientific heroes, Alan Turing, where in the last paragraph of his nice paper involving AI, where he brings the Turing test, which is known, he's saying in the end, we can only see a short distance ahead, but we can see plenty there that needs to be done. So thank you for your attention, and if you have some questions, and I can try to help to answer. Thank you.
Thank you, Professor. Very interesting talk. So while people leave their questions, if you have any questions, please write them down on the chat box, or you can raise your hand and I pass the mic to you. So first, a quick question concerning the initial sampling of structures that you need to start building these models to describe. How crucial is it, the number, and what structures are included in this initial sampling for the model to be successful and efficient?
So the initial database or the initial population, right?
Yes.
Yes. Okay. Yes, it's quite important. The way you design your initial database, it's quite important. In these results that I have brought to you here, I just made that randomly because I wanted to test the algorithm. So those were randomly, and of course, this random process of getting the random defects, in this case vacancies, or even the molecular clusters, of course we have some algorithms to do that, to be not that bad because they can collapse and things like that, but it's random in the beginning. But of course we can improve that by considering more chemical sense during this random initial population, but they are random.
Okay. Yes, but you need to see this. You think that some chemical intuition must be used to increase the efficiency of the selection, and also I think that is there the risk to be trapped in some configurations if you don't include diverse enough sampling in this initial step.
So you mean if I don't know if I could follow the question, but of course we can use a chemical intuition. I mean, we can try to develop algorithms or even chemical sense to create the initial database. And the active learning algorithm is quite efficient, and the sampling is quite important because, for example, in the case of the vacancy, we have a discrete search. So actually, we can somehow map all the possible vacancy configurations. When we have the atomic cluster, for example, we have to use GA operators to get a better unexplored space to apply the active learning. So when we have vacancy, actually it's not much a problem, just sampling, because it's a discrete search. but we know the sites where we wish to remove. But when we have harder problems like continuous search, which is the case of atomic cluster or molecular clusters I have shown, actually we can have some traps if we have some collapses of molecules. But of course, we must guarantee that during the evolution of the populations, we eliminate those structures that are strange, like closer in atoms or too far.
Okay. Concerning the vacancy, the work about vacancies, I'm not sure if I follow it correctly, but during the search for new structures, is it only the site of the vacancy that is changed, or is there some local optimization of the structure that considers atomic displacements?
Yes, it's a great question. Let me just return. Okay. Okay, yes. When we perform the vacancy, so for example, we are going to remove Gs and the Gs and the Gs. We remove the 3 of them, or 4, whatever. And we model our problem in a rigid structure. But we perform for the target the local optimization. I mean, the machine learning is built in a rigid structure, but the total energy comes from a local optimization. Of course, in this case, the molecule deforms a little bit.
Okay, so the machine learning model can consider these displacements to compute the energy.
Yes. Of course, it won't be perfect because I lose a little bit information from the descriptor, because the descriptor comes from a cage fixed, and I have the total energy, which is the target, from a local, from a small different structure from the local optimization. But it's good enough to do this global search.
Okay. I have a few questions also concerning the codes that you showed. Are they available for distribution? Can you say something about it?
Yes. We haven't provided yet because we have a lot of work done. But if you wish, we can. So far, even written in the papers, just by email, I can send you the code. But we are going to provide a website and things like that.
Do they have a direct? Do they have a direct interface with some codes that you showed us for compute the DFT calculations? Or?
Yes. We have, I forgot to mention, both the GAMaterial and the QMLMaterial, they have interface with the DFDB plus software, with Daemon 2K, with Orca, XTB, has interface with QuantoExpresso. VASP, I don't have this interface because I don't have the VASP license. And but we have these interfaces from quantum chemistry codes.
How easily do you think it's for if I use VASP, for instance, to put data from VASP in this code? Is it a hard task, or is it the right thing?
Yes, no, it's easy because actually what the QMLMaterial or GAMaterial do, what they do is just to do I/O in the output of the software. So we just need to know how to, of course, how to run the VASP. I don't know, actually, I haven't run the VASP. And after running that, of course, we have to have a template input, and we run. And the structure that will be in this template input, you come from the active learning, and the VASP will compute. It will be called within the QMLMaterial. The VASP will run, and we will have the final output. From that, we get the energy and the final structure. It's quite easy.
Okay. So, okay, so it seems we do not have any further questions. So, thank you again, Professor, for a very nice discussion and for accepting this invitation. I think I hope we can stay in touch in the future. So, thank you again. So, let's end this meeting for today. Thank you.
Okay, bye-bye.